Yeah, have you clicked go live on your OBS?
Start streaming, and
It's gonna probably have some delay before it shows up in YouTube. It shows that you are connected. Oh, yeah.
There you go.
Yeah.
Yeah.
there's a bit of a lag currently.
How much lag is it?
Okay, I'm gonna turn something on now.
Turn towards me. Oh God. That is a few seconds, isn't it? You're gigging Wi-Fi, so it shouldn't be the Wi-Fi that's causing that lag.
Yeah, it's, I guess, what we can expect YouTube streaming.
Wait,
Then-
maybe I can. There is a switch for.
It doesn't matter anyway
Yeah, there's a switch for.
Well, it matters for you.
for us in here.
Yeah.
There was a switch
Yeah.
for. Oh no, I can't set it. I cannot set it anymore. There's a low latency, not low latency, but I'm not sure it anymore. But I'm not sure if that would help.
Just put your hand up in the air, Declan. Just put your hand up in the air. Just put your hand up like this, so we can time.
It's right. Okay. I actually just deleted that video source. Video capture device. Okay. That's too much. So maybe the only way we can all do it is I turn off the video, and the only way you're going to see is either with that lag, or if you want to see my screen.
15 seconds. Is it anything to do with all these different screens you've got open? I mean, this is saying, when you look at this screen up here, it says that you've got like 50 windows open or something.
There's like 2 minutes behind at least.
What if we?
That's the mirror of the recording when I'm capturing the screen, and it's capturing itself.
Oh.
So I've got 4 windows open.
What if
I guess.
we connect it through the adapter? Maybe it will work if it's connected through this thing. Do you have USB-C?
Yep, we have
Maybe we
USB-C.
can try it.
Okay, USB-C video.
In the worst case, I guess there are only like 4 of us, so we could crowd around.
Yeah.
I guess.
Let's see what happens with this.
Oh.
Is it still streaming, Yaroslav?
Yeah, it is.
Okay. ready. Okay. So, sorry about the technical difficulties. So this presentation is about calculang, which is a language for calculations. So calculations, calculang, and in calculang we write pure functions without side effects. So pure functions means that the same input into a function gives you the same output, a predictability that's useful to reason about calculations and numbers. And no side effects means that this isn't a programming language where we tell the computer to do this, do that. Rather, we're only concerned with describing calculations. If there's no side effects, then how do we do things with our numbers? To do things, we bring our own language, which can call numbers from calculang rather than re-implement them. And this gives us this nice separation of concerns. Calculations and calculation logic separate from general programming and application logic. And for these calculations, then, it means that they can have their own life. They can be used in many different applications and tools. And these applications and tools can be written in any programming language. Calculang is only doing computation. It's not opinionated about what happens with the numbers afterwards. And since we have a language just for calculations, then we can add features that help us to structure and manage our calculations and numbers. So I mentioned before how numbers and calculations can be used in different applications and tools. They can also be used in a flexible way in other calculation models. So this is a key.
Sorry, your source is not selected correctly.
Right, so that hasn't changed at all, has it?
Yeah, it's stuck on
Right. I thought that was just lag when I saw it.
It's been like this for a while.
Right. That's kind of the best I can do. That's got a big lag, so I guess it'll take a minute to see it.
Oh. Yeah, it should show up soon. Yep.
Yep.
So calculations can be used in different applications and flexibly in other calculation models. And this is really the only important technical feature about calculang, but it's what I think helps us. I think the flexibility is what helps us to provide good structure for our calculations and numbers. Here I mentioned functions, as in pure functions with a background in functional programming and in maths. But we also call these formulas, which have, as a term, it has a similar background, and it also is something that spreadsheet users are more familiar with. And I think that spreadsheets are a useful benchmark for a language for calculations. Arguably, spreadsheet formulas are the most widely understood programming language out of all. So I want to show you some points about calculang from the calculang website, calculang.dev. So here you can see the logo, the aims of calculang, which are to be shareable, communicable, transparent, verifiable, understandable, concise, flexible, and reusable. We care about these things for numbers. That's all we're concerned with. For their calculations, their numbers, and the workings of those numbers. And a language for calculations should be portable. So calculang compiles into JavaScript, which is highly portable. I use it inside some of my blog posts. Sometimes you wouldn't know it. You can put it in dashboards, banking apps, or websites, whatever. I mentioned transparency and flexibility. In calculang, formulas, or those pure functions, they're the building blocks of calculations, and they're the mechanism to provide flexibility and transparency. Here I have a little opportunistic steal comparing spreadsheets. Mainly in a spreadsheet, your calculations and your calculation model is tied to layout. And in calculang, you're free from layout, it's a separate thing. So certainly refactoring is easier, and flexibility. And everything in calculang has a name, so that, like, even in a spreadsheet, even the formula functions are tied to layout, as in horizontal lookup, vertical lookup. So in calculang, you refer more using a name. And mainly, formulas are code which can work with state-of-the-art tools and controls around code, where in spreadsheets this is more of an issue. And this is the last point I want to get to about tools. So I'm going to show you some tools that I made, and they all use this introspection API for calculang, which is free to make tools with. More so than the tools I show you, there are other tools that can be made. Down here we have some examples from finance. So illustrating usually interactive and visual interaction with numbers coming from finance models like loans and savings. And down here some simulations of different things, some methods that are used in games. A very simple climate model here, and maths art, a few examples about that. And down here we have shop modeling, which is just something I use to illustrate some concepts about calculang. We're going to look at these, but I'm going to do so using a new environment that's eventually going to replace this. But for now I'm going to change to this. This is online, so you can find it too. So this might be your first time to see calculang code. But the first thing to notice is the separation of concerns. I'm presenting two different things in separate places. On the left we have calculang code. On the right, separate code base. It's JavaScript. Visualization and interaction with numbers that come from the calculang model. And it's mainly here that I want to show things. I'm not so happy with this visualization on the right, but it's just going to be hopefully help us to help me to make some points. Now, looking at this model, it's a model that takes, supposing you're a shop and you buy something for some purchase price and you sell it for some sales price. You do this for some number of units and you have some amount of expenses. This is calculating your profit. And like I said before, as in formulas are the building blocks of calculations, we have separate formulas for sales and purchases. So we can read these formulas. Sales is units times sales price. purchases is units times purchase price, and profit is sales minus purchases minus expenses. So these are the only two new calculang primitives or calculang constructs, formulas and inputs. So all these formulas have a blue background and these inputs have a pink background. And another thing to notice, units is an input and sales is a formula, but both are implemented as functions. That's important so that we don't need to refactor so often between inputs and formulas. That's what we want to avoid for flexibility. And another thing to notice, because everything is a function, there's a lot of brackets. Brackets, brackets, brackets. I don't know, 10 or 15, I guess. I didn't count them. There's a lot of brackets when we're working with functions. What's weird about these brackets? Anyone? So there's nothing in them. So they're redundant and they annoy people, but they're there for now. What calculang does is it keeps track of how inputs are used, and it populates these brackets for you. This is called input inference. We can see this when we click here. So calculang determined that sales depends on units and sales price, and purchases depends on units and purchase price, and it threads these inputs all the way to where they're needed. Now looking at the right hand side again, this is kind of showing us a very naive output. We're looking at some number of units, some purchase price, some expenses. We're buying for, say here, the sales price is here. So we buy something for 5, we sell for 6, we do this 20,000 times, and we've got 15,000 expenses. Then our profit is 5,000. But this is telling us, this is showing us that if we just keep increasing our price, we just keep making more money. But in reality, your boss might want to see an allowance for a demand curve, lower sales if you increase the price. Maybe he's interested in changing it. So he might get the marketing department to give you a demand curve, which might look like this, where, okay, 20,000 is our sales, that's price point 6. If we go to 7, we can't sell anything because of competition, and a linear drop between here and there. And if we want to allow for this demand curve now in our entire model to get an allowance inside profit, we do that in calculang like this. So units is an input. We want units to be constrained to the demand curve, so we say units is demand curve. We can move that up because it's no longer an input, but that's just cosmetic. So our entire model reflects this change. And units, which was an input, obeys this demand curve. Everything which depends on units obeys that demand curve. We can look at the output here. So units was an input, but all these references to units now depend on sales price, because sales price determines the demand curve, which determines units. Now this looks kind of convenient because there's a whole load of code here that we don't need to manage. Calculang does it for us. It's delicate. This input threading is a very delicate thing to do. So it looks convenient, but that's not the purpose, or that's not the reason it's there. The reason it's there is because of flexibility. We need it for flexibility. We'll see that next. So there's something I really don't like about how I implemented this change, which is I just butchered this model. And sometimes models are very precious, and they should be. So you would at least want to take a copy of this and butcher it, but that has its own problems too. So in calculang you can use modularity, and I'm going to show you an implementation of this change using modularity now. So so the model changed here, but you didn't notice it because the numbers are the exact same. Now we are importing the calculations that we want from the original model, which is in this file, say. And we're seeing that this is a demand curve and units equals the demand curve. If we look at this file, this thing that I said was the original thing, it is the original thing. There's no concept of a demand curve within these formulas. But because calculang gives precedence to formulas that are defined closer to the entry point, so it gives precedence to these formulas when it makes these calculations. And in that way we can say, I want these calculations, but with these changes. So that's, when we do this, if we look at what we need here, so in here you can see exactly how this is implemented. So we import those there, we import the demand curve in units from the top, and we rename this, and now units refers to the original, but sales depends on sales price. This is the same code as that we started with. What we started with, units here depended on units because it was an input. So it's because of flexibility that we need input inference. And this helps us a lot to structure things. Some examples of where I've used this are they're indicated in the calculang.dev gallery with this here sign. So this is one of the important ones. Some of these are I'm using modularity just to separate calculations. But this is a particularly interesting one to look at. We won't go into detail on it. And so is this one, which is a calculation supposing that you're the Minister for Finance and you're changing tax rates. It takes one calculation for income tax, it calculates a calculation for a population, and then it replicates that twice for a set of, say, current tax rates, and then a set of tax rates you can change. And it does all this without copying any code. It has other little flaws, but that's the structure that I was trying to get. It was the first early test of this. Another place where I use it is on my blog. Inside here, to visualize risk. So this is calc.deck.dev, my blog. And in this post about visualizing risk, I take a pension calculator projection, which is this, but for the purpose of understanding the risk, I change the investment returns from being something you give it to being something that's random, and that way I get a completely different behavior out of the model so that I can do Monte Carlo simulations. The pension calculation in this is the exact same as the pension calculation in here. So this helps us to write code which is far more maintainable. What I went through here about input inference and modularity is the really hard technical stuff about calculang. If you get that, you get all the technical stuff about calculang, but there's more to it. So earlier I mentioned transparency. This here is a different environment, older, but has some features I'm going to use here. This is a savings calculation on the right, savings calculator. On the left we can change some inputs. For supposing we're saving 1,000 for 5 years with some interest rate. We end up with 5308 because of interest. In this environment we can click on balance, and we see the formula. We can click on interest and we see the formula. And I remember when I was in school, I was always told to show my workings. For a computer, this should be really easy. So now you can see an overlay of the workings behind the number, for any number we're interested in. And we can also navigate through these numbers just by clicking them. So 5308 is 5204, click here. 4121 plus 1000 plus 82. And just by clicking we can navigate. 40.40, what's that? It's 2020 times 2%. That seems to make sense. 20 is calculated by 1000 times 2%. All these workings respond to changes we make to inputs as well. And that's all right for numbers that are in this environment, but a lot of numbers out in the world are elsewhere. So this is an imaginary piece of paper. There's a lot of paper like this with important numbers in it. It's telling you that for borrowing 100,000 at an agreed rate for 10 years, 12329 is an important number, which was calculated. And by using this, which connects these inputs to a model, you can check that number. $12,329, and you can navigate the workings as before. And I don't want to convince you if this is right or wrong, but the purpose of this is just to show a way to share not just the number, but using a language for calculations, also to share the calculations and the workings. So one more example of using this type of environment is here. We have a bar chart here. It's a bar chart of a world that we can move around in. And the calculations are from the calculang model on the left. Go into the corner so that when I turn around I'll have a nice view. But I got stuck. So how this works, we can look at some formulas. So we have a formula for the map. This describes the world that we can see also here. Formula for looking up the map at different points. But how this works, visualization, is here we can see the world, and we can see the player, this arrow, and we can see a field of view, the field of view of the player. And to get this bar chart resembling the world, we split the field of view into many different directions. And we cast imaginary rays in each direction until they hit a wall. And rays like these, to travel far before they hit a wall, we give them small bars. Rays like this that hit a wall at a shorter distance, we give them bigger bars. And these green bars are really big because they're caught by this green block, which is partially in our field of view on the right. And we can use the left hand side to navigate the algorithms that are going on here. So we're plotting ray inverse distance, and if I click, this brings me right there. And this is reactive in updates as I scan. And when we go in, we can see this is the minimum of two different distances, and there's a multiplication by something, and I'm not interested in that, so I'm going to turn that off. Fisheye correction. So the minimum of 2.56 and 6.58 is 2.56. This is using an algorithm that takes advantage of the fact that you can only hit a wall at a vertical or horizontal grid line. The very first time I implemented this, I went with a naive approach. What I did is I traveled along the way for a very small interval until I hit a wall, so I had to do it many times, constantly checking if I hit walls. This algorithm just checks intersections with grid lines. So here I'm looking at the vertical grid line check. So we check the first vertical grid line in front of us, which is here. We check the next one. There's no wall, so we continue. Yeah, there's no wall, so we continue. And here there's a wall, so we stop. We do that for the vertical grid lines too, and we take the minimum because we want to see the wall that's in front of us. A nice thing about this environment too is that you can change the world without resetting or recompiling and starting again. What I'm showing you here and here is a connection between numbers which come from computers usually, a connection between them and their formulas and their workings. And the thing that facilitates all of this is this. That's what I showed initially. The separation of concerns means that we can point to code which is just about calculations. The purity means that to check a number we can just run it again. And these are the same things that help us towards calculang's aims, which are to be shareable, communicable. To be shareable and communicable, as regards numbers, it helps that there's code that's just for numbers. To be transparent and verifiable, it helps that you have that purity and you can just run things again. To be understandable and concise, it helps that there's no programming logic mixed in with your calculation logic. And to be flexible and reusable, that's what I went through about input inference, the technical stuff. And that's all I have to show you right now. One last thing about this here environment. This is going to replace the gallery, so I'm putting more examples in here. But this currently looks like a over-engineered graphing calculator, but just to show you that here we can see two outputs the calculang gives you. One is the JavaScript module, so that's to emphasize that you can use this model virtually anywhere. And this here is the introspection object, which tells us everything that the calculang compiler used to determine all of its relationships and more to help to make tools. And it's what I use in all of these tools that I showed today. So that's all for me, and if anyone has any questions, I'll be happy to take them.
So the syntax, can you show the syntax again?
Yeah.
So what goes after the formula's name is basically JavaScript's syntax for lambdas, or
Yeah, it's JavaScript syntax for functions which
anonymous functions.
are anonymous. Yeah.
Can you put anything in the round brackets after equals? Does that serve any purpose for additional definition?
As in, like this?
Yeah.
No. If there's a use case for it, perhaps, but that's what you need to put in there is inputs for your calculations, and calculang manages that. So
Have you considered simplifying the syntax?
I would, yeah. Now, so I always, every time I show this code, people ask about the brackets. It's redundant. Export const is redundant. Yeah, I'm not in a hurry to do it, mainly because also this has a nice mapping to JavaScript.
Yeah, so you want to keep compatibility with JavaScript with this.
Yeah, it's just convenience for now.
Does this let you use a JavaScript parser rather than writing your own? Is that the
So one point to both of you is you can use JavaScript in this. You can run JavaScript, and but like you should not really put JavaScript in this file. You should put it somewhere else and import it. So and then I don't. The compiler has a parser and all this crack. It uses Babel, but I put legit JavaScript that you can run in whatever runtime you want. So does that help, or?
So how do you set up an input?
So by a convention. So an input, if calculang sees the name of a function with underscore in, that's convention to indicate an input. You can put stuff like this in there too. So it's just a convention using a function too.
So in the early slides you mentioned Python. I missed a bit of the beginning of the talk because I was setting things up. Does it have compatibility with Python too?
And no, the idea is like, I thought this would be easier, but the idea is your JavaScript can run through a runtime that you can use in Python. I've run calculang code directly in Python using, there's many options, but I haven't found, there's no one definitely better one. So you're effectively running a V8 runtime. And different languages have different ways of doing that. And maybe it's heavy, maybe we could output different languages too, but for now that's what you would be looking at if you wanted to. And alternatively, you can run calculang models, save them to files to read, or different ways. I haven't done I thought I would do more Python integration stuff, but some of the things I want to do in Python, I'm doing now in JavaScript.
That core code you showed earlier, so does it include a link to one of these apps and inputs, or how does it work, this core code?
It works by just linking to this environment, and it has these inputs in it.
So it contains
The QR code. Sorry.
Yeah, it contains the link to this environment and its inputs.
Yeah, and that's really just for demonstration purposes. And like one of my earliest like a feature I want to make is a Firefox or Chrome browser extension, so that when you're on a page, this might not be good for everyone, but it would further illustrate separation and other things. When you're on a page, you could have a button up here that lights up if there's a calculang model. You can then go away and do your own investigation about how it works. So when you're, for cases like this where you're reading a blog, I don't want to show everyone the formulas, but I want them to have access to them. You have access to them down here, but we could provide a simple user interface like these other ones that's general, that you can access with a browser extension. Important where numbers are used to communicate and to influence, and in the media, if you're reading something about numbers and they've exposed a model, could give people a chance to interact.
So Andrew, how does it, for doing the calculations, does it like form a directed graph of all the formulas? And if there's a loop, does that blow up or like dependency?
So I do a lot of recursion in this. So I don't think that the compilers can blow up because of recursion, which makes sense. The runtime might blow up, and so that's going to be an issue you're going to deal with there. I don't do anything like checking for, but it essentially, the compiler itself is only 1,000 lines of code. It's mostly a little bit of graph theory. I don't have right here. I actually do. In calculang.dev, you can click on an example, and under this DevTools thing, this collapsed, you can see, you can download this graph of all the inputs flowing to formulas to see that.
Yeah, I guess if you have it explicitly construct a graph, you could do a cycle checking, or you could like hash or keep a set of all the states you visited or the formulas you visited, maybe.
Yeah, I guess recursion is a thing that will, in a spreadsheet, we write recursive formulas naturally without knowing how hard it is, because we have layout to help us. Like if we make a cycle error, we're going to see it much quicker than in abstract code. So that's a problem that does need a solution. Okay. So thanks everyone for your time and patience.